everybody. Happy June 1st. We are starting our nuclear chemistry unit and a few background bits of information for you. First of all, this course has been largely focused on chemical reactions. And as a reminder, chemical reactions involve the transfer and or sharing of electrons. Now we're moving on to nuclear reactions, which involve changes in the nucleus of atoms. So that means there's going to be changes in the number of protons and the number of neutrons. And when we change the number of protons in particular, we would change the identity of an element. And that is called transmutation. Okay, so when we're talking about nuclear reactions, we are talking about unstable nuclei. And all elements that have more than 83 protons are unstable. So they're going to naturally or spontaneously decay. So here we go. We're looking at here polonium and larger atoms are all unstable. Now, the purpose of the decay of an unstable nucleus is for it to become more stable. And it becomes a different element. It's transformed. And in the process of that transformation, radiation is emitted. So we can also state that these are parent nuclides, these unstable nuclei, and the stable nucleus or relatively stable nucleus is the daughter nuclide. Okay, and there's several possible forms of radiation depending on the type of element we're looking at. And we're going to look at that in table O shortly. So here we have, I've blown up table O a bit for you to see. These are very common symbols used in nuclear chemistry. And when we're talking about radiation that's emitted, these are the options. You could have alpha particles, beta particles, gamma radiation, or positrons that are emitted. We have neutrons and protons listed here because these are going to be important, right? In the sense that the neutrons and or protons change in number. So let's just start from the top here. An alpha particle is the equivalent of a helium atom. As a reminder, that's the mass of 4 and the atomic number is 2. That's the number of protons. Another way to show an alpha particle is to have this alpha symbol with a 4/2. Now, beta particles are electrons, the equivalent of electrons. That is 0 over a -1 charge, little electron. It could also be shown as the beta symbol with 0 over -1. Then there's gamma radiation, and that's symbolized by the Y with a 0/0. There's no mass and there's no overall charge. Neutrons, if you recall, neutrons are normally found in the nucleus of atoms, all atoms except hydrogen, by the way, right? And it has a mass of 1 and 0 charge, neutral. Then we have our protons. This is the equivalent of a hydrogen atom. Why? Because hydrogen atoms do not have a neutron. So a hydrogen atom has a mass of 1 and a charge of +1. And then finally, the positrons. These are positively charged electron equivalents. 0 mass, positive charge, could be represented by an E or a B. So these stars represent radiation. And radiation can be particles, or in this case, it would be electromagnetic rays. These are not particles with great gamma radiation. and a positron is a particle. Okay, just taking a quick look at our electromagnetic radiation spectrum. I highlighted here gamma rays. So we have very high frequency gamma rays, and their wavelength is 10 to the minus 12 meters. And their approximate scale of the wavelength is at the atomic nucleus level. Another thing to be aware of, these three forms of radiation have varying penetrating power. So for example, alpha particles have low penetrating power, which means that they're not as dangerous for life. So an alpha particle, as represented by that helium atom, actually cannot penetrate paper and cannot penetrate human skin or other animal skin. So that means it's got low penetrating power, whereas beta particles have what we would consider a moderate penetrating power. They can pass through paper, but aluminum would actually prevent them from passing further. And these actually can penetrate human skin or other animal skin. So these are a little more dangerous. Finally, gamma rays. This is very high penetrating power. Remember, these are not particles, so they have these wavelengths that can pass through paper, through aluminum, and there is a possibility that it could even pass through lead. However, I want you to think about that lead a little bit. When you go to a doctor's office or the dentist, they have you put on a lead apron because this is a good substance, if it's thick enough. It is a good substance to prevent X-rays, which are closely related to gamma rays. And if we just take a quick look back at the electromagnetic radiation here are those X-rays. Gamma rays have even greater penetrating power than X-rays. All right, so these are very dangerous. So let's talk about these radiation forms. They are considered to be ionizing radiation, and that means they can harm life. And ultimately, I hope you can recognize what molecule this is. This is DNA. This is our genetic blueprint that's found in the nucleus of our cells. What else can ionization do? Ionization of tissues disrupts cell function. It could actually kill cells, and it could mutate DNA. Now, an additional concern is if the DNA mutation is in sperm or eggs. If those organisms reproduce, that mutation can be passed on to the offspring. Okay, so I would like to just briefly introduce you to table N at this point. You will be using this throughout this unit, but we have some examples of nuclides, and we'll talk about the concept of half-life in a next lesson. Here's the decay mode. So just to connect that, the decay mode correlates to, is it alpha, beta, gamma, or is it a positron? Okay, so we're going to start looking at some examples of what we call nuclear equations. So we always know here, in this case, this is the parent nuclide. So when radium decays, it releases or emits an alpha particle, and it gets transmutated into something else. So what you need to do is you need to balance mass and charge when we look at nuclear equations. So I have a mass of 226 here. I have a charge which correlates to the protons. So this side of the equation must equal 226 and 88. Well, we have 4 here. So 226 minus 4 is 222. Okay, 88 minus 2 is 86. How do we identify what X represents? We must always look at the number of protons. So when we look here, we have radon, 86. This is the daughter nuclide. Now, I'm not saying this is very stable in and of itself, because it's got 86 protons. So this is radioactive too. But so what could happen is this would undergo another type of decay and become even more stable in there. And just as a side note, what happens when we have an alpha decay? The atomic number decreases by 2. Why? Because that 2 is represented by the alpha particle. The number of neutrons and protons also decrease by 2. And then finally, the mass number is going to decrease by 4. Well, this time we're going to use an example of beta particle decay, or just beta decay. Now I have a little side note up here. Okay, this is representing how we get this beta particle. Even though it's the equivalent of an electron, this is not from those valence electrons that we've been studying throughout the years. This electron has been generated from the nucleus. So as a neutron in the nucleus decays itself, it creates that beta particle. So let's look at this example with lead. It's going to undergo beta decay, and we have to balance the mass and the charge. So this must be 214, correct? And then 82, and this is a -1, this must be 83, because 83 plus a -1 gives us 82. So then we go and we look, what element is 83? That is bismuth, and that is the daughter nuclei. So in beta decay, you're going to notice that the atomic number actually increases by 1. The number of neutrons decreased by 1. Why? Because this neutron decayed to form that beta particle. And then finally, the mass remains the same. Why? Because there's no mass. There it is. It's a little electron equivalent. Let's move on to another example. This is of a nuclear decay. This is a positron emission. Just to take a quick look. Oops, let me uncover that. Just to take a quick look, here's our positron. It's 0 over a +1 electron equivalent. These, again, these are not electrons that are in valence shells. This electron is generated by an unstable proton in the nucleus. We look here, so again, we're going to balance that. 37, here's a 0, this is a 37, a 19, and a +1 is an 18, right? 18 plus 1 is 19 on this side, balancing that. Let's look it up. Argon. Now, when we look at this, what happens to the atomic number? It decreases by 1. What happens to the number of neutrons? It increases because that proton decayed. Finally, what happens to the mass? It remains the same. Why? Because there's no mass to that positron. Let's look at this example. This is gamma emissions, tenectium. We have 99 over 43. It's going to decay, releasing a gamma emission, which is highly penetrating emission. So this is dangerous, even more so than the other examples we've talked about. X must be 99, and this must be over 43. Oh, very interesting. Guess what we have? we didn't actually have a transmutation. Okay, I've lined up all of the examples that I just went over because I want to make an important point. These are all examples of natural or spontaneous transmutations or decays. And we're going to know that this naturally happens because there's only one species on the reactant side, and it emits some form of radiation. These are all natural decays. So let's look at some artificial transmutations. That is where in a laboratory, scientists could purposely bombard the nuclei of atoms and forcibly bring about a transmutation. So it's considered artificial. And in artificial transmutations, you will always have two species on the reactant side of the equation. So we have two species here. So we have a nitrogen parent nuclide that is purposely being bombarded, so shot at with high-speed alpha particles to disrupt its nucleus. And what happens? You have a proton released. Well, the same thing like before, we have to balance our equation. We're going to look that up, and we have the daughter nuclide as oxygen. Let's look at one more example. So we have aluminum being bombarded with a neutron in this case. It's going to form or be transmutated into sodium. And what else? 4/2. Well, by the way, here it is, helium, 4/2. Or again, we just look right here. I hope you enjoyed this lesson. Thank you. Have a great day. Bye.